Okay, I think we should be ready to start. So first of all, greetings from Vienna. My name is Stefan Jakšić. I work for Austrian Institute of Technology, and I would like to wish you a warm welcome. This is the Temporal Logic session of RE 2020, held virtually, and we have 5 very interesting presentations today. After every presentation, we have, of course, the Q&A session. We're looking forward to your questions, of course. So we start with the paper on logical signal processing, a Fourier analysis of temporal logic, written by Niraj Basnet and Hussam Abbas from Oregon State University. So let's start with the first presentation for today.
Hi everyone, I'm Hussam Abbas. I'm an assistant professor at Oregon State University, and this is work by my student Niraj Basnet. So the starting point for our work is the following setup. Suppose that you have a buoy out in the ocean and it is measuring, for example, wave height, which is an analog signal, meaning continuous time, continuous range. And in this work, we're only interested in analog signals. It wants to transmit the signal to some central station where it will be monitored against a temporal logic formula phi. So to do so, it first compresses the signal, it transmits it, the signal is reconstructed at the receiver, and it is monitored by the TL monitor. And the output of the monitor is itself another signal because we're interested in quantitative semantics of temporal logic rather than Boolean semantics. Now, compression is a lossy operation, so it is natural to ask, how does compression affect the monitor's output, right? Because we lost some information, did we lose any information that is relevant to the formula? Did we change the verdict of the monitor dramatically? Now, since in signal processing a lot, if not most, compression algorithms operate in the frequency domain, another way of asking the same question is, what input frequencies are relevant to a temporal logic formula, right? So you can see here in this signal, there are some low frequency variations that I am drawing, and there are also, of course, some very high frequency variations. Well, which ones of these are relevant to the formula? If the compression algorithm says, okay, I'm going to eliminate everything, all signal content above 100 Hertz, what does that do to the monitoring output? How badly is the signal affected? Is the output signal affected? Right now, we have no way of actually answering that question because we have no way of determining what is the frequency content of a temporal logic formula. And that's a big problem because many operations in signal processing do happen in the frequency domain. Now, this question about frequency is an example of a broader question I'm interested in, which says, in cyber-physical systems, you have an interleaving of signal processing operations like compression, sampling, filtering, enhancement, denoising, etc., and logical operations like temporal logic monitoring. And I'm really interested in understanding how we can analyze the interplay between these two types of operations, which is the project I call logical signal processing. So, to answer this question, now, existing work doesn't really ask the question or answer it. The closest work to ours does establish some formal similarity between certain logical operations and, for example, convolution, but the question of frequency content hasn't been raised. And this is the contribution of this work. To start answering the question, let's get concrete a little bit. We are working with specifications in past bounded signal temporal logic, which is the past version of STL with bounded temporal operators. So you have the once operator, which says at some point in the past in interval I, phi is true. You have the historically operator, which is the past analog of always, and you have since. So phi 1 is true since phi 2 has been true. And as I said, we're not looking at the Boolean semantics of past bounded STL. We are looking at the robust or quantitative semantics. So we are measuring the robustness of a signal relative to a formula. And the robustness is computed. So robustness is an operator which takes in a signal to be monitored x and puts out another signal, rho of x, and its value at time t is computed using the usual quantitative semantics. And it is important to highlight or stress that we are thinking of robustness as an operator, which maps signals to signals, and it is, of course, a nonlinear operator because of the max and the min that are in there. And I want basically, once I think of it as an operator, I want to say, what is the frequency response of this operator? It might help to think a little bit in analogy or to remember what we know about the frequency response of linear time invariant systems. So you might remember an LTI system is characterized by its impulse response. Given the input signal X, the output signal Y is the convolution of X and the impulse response H. And I can study the system by looking at H in the time domain, but I can also look at the frequency response of the system, which is nothing but the Fourier transform of H, and which is represented here. So roughly, I'm hand waving a little bit, this says that for this system, frequencies below 1 Hertz are important because you can see they are assigned of a weight of around 1 or more, and frequencies above 2 Hertz can be safely discarded without changing the system's response too much because they are suppressed. They are multiplied by something less than 0.8. Again, I'm hand waving. The exact values here aren't what matters. So in analogy with this, now, since we are thinking of the formula in terms of its robustness operator, and the robustness is just a nonlinear operator, I want to get, quote unquote, its frequency response. But because it is nonlinear, it doesn't have an impulse response, etc., so we have to do something more. Now, we immediately encounter a difficulty just dealing with atomic propositions. If we ask what is the frequency response of an atomic proposition, the robustness operator for an atomic proposition P, we immediately hit a difficulty. Because, for an atomic proposition in STL or past bounded STL, the robustness at time t equals some arbitrary function mu of x of t. Now let's suppose mu is identity, right? Let's forget about mu, it's irrelevant really. When we say I want to measure x of t, we're saying I have an analog signal x and I want to access its value at a specific moment in time t. This is a measurement, in signal processing terms, this is a measurement of infinite resolution, infinite bandwidth. Not only that, it also requires infinite energy to do it. Now, if I'm thinking of monitoring as just another signal processing operation, right? You have a filter, then the monitor, then another filter, and I say, oh, by the way, this box here requires infinite energy and bandwidth, well, then the entire analysis crashes. It becomes trivial or useless. That's why we have had to introduce in this paper a new logic, which we have called bounded bandwidth signal temporal logic, or baby steel. And it's really very similar to past bounded STL, except at the atomic propositions, for which we now use finite bandwidth measurements. And the details are in the paper. So everything that follows uses baby steel formulas. Now the strategy is, we will first approximate this nonlinear robustness operator using something called finite Volterra operators, which is another kind of nonlinear operator, but for this one, we have a well-developed Fourier theory. And so the technical challenge is in doing this approximation. So what is a Volterra operator? A Volterra series operator is of the following form. It takes in a signal x, it puts out a signal y, and the value of y at time t is this, what you see in front of you, a sum of integrals. So this is the constant h0 plus the integrals h1 tau x t minus tau 1 d tau 1 plus this other integral, and now we have h2, which is a two-dimensional function, and there is the product of x with itself, d tau 1, d tau 2, etc. So you see this here is nothing but the convolution. So this is the linear response of this operator. And starting from the second order, we have the higher order nonlinear responses. And I would want to draw your attention to the h's. These h's characterize the finite Volterra series operator. So if we write hn to be the Fourier of hn, we can obtain the output of this Volterra operator in the frequency domain. Specifically, it is given by this. So the output y is given by this sum, and y sub n is an integral of this form. Now, the specific integral doesn't matter for the talk. I just want to draw your attention to these generalized frequency response functions, which remember, this is the Fourier of h sub n. So if I know that h sub n is 0 for a certain range of frequencies, omega 1 through omega n, then I know that this entire thing is going to be 0 in that range of frequencies, which tells me that this range of frequencies is irrelevant to the output of this particular operator, finite Volterra series operator, right? So this is the way we get the frequency analysis. So now going back to our strategy, if we approximate the robustness operator using a finite Volterra series operator, I can then obtain the Fourier transform of this Volterra operator. And these generalized frequency response functions are the Fourier analysis. They provide the frequency content of the temporal logical formula phi, right? This is how we get it. And so now we can get the output of the monitor in the frequency domain, etc. Now, I should point out here, obviously there isn't a whole lot of time, but I should point out that really the key technical contribution in the paper is in establishing that the robustness operator for any baby steel formula can be approximated arbitrarily well by a finite Volterra series operator. Which, if you think about it in general, I mean, this is what a Volterra operator looks like. There is no reason to assume that, or to expect perhaps, that the robustness operator can be approximated by a sum of integrals of this form. Turns out it can, and so the details are in the paper. All right, so this is broadly our strategy and how we went about it. Now let's see a few examples. So the first formula is once C, right? So this is the past analog of eventually C, where C is some atom, some finite bandwidth atom. And from left to right, I increase the value of T. So this is once C for increasing width of the temporal interval. And on the first row, we have the first order response. On the second row, we have the second order response, which is a two-dimensional function. There are other, higher order responses, but I'm not showing them. So you can see that as you move from left to right, as you increase the width of the interval for this formula, it starts suppressing the higher frequencies more and more, right? So the first order response suppresses higher frequencies as you increase the width of the interval, suggesting that it is looking at low frequency content more. If you look at the second order, for the first column, basically the second order is practically zero. So dark blue means zero, whereas golden and yellow means non-zero, basically higher values. As you increase the width of the interval, we start seeing some response at the higher frequencies. Here, here, and here. Now, I don't want to overinterpret this too much. What does this mean? The point to be made here is that there's simply no way, in my estimation, that one can look at this formula once C and guess, oh yeah, I can tell what the frequency content is. I can tell which frequencies I can discard safely and which frequencies I need to preserve. That's why we need a systematic, rigorous Fourier analysis of temporal logic, right? It gives us this ability to do this. Now here's a more complicated example. We have a formula with embedding of operators. So it says A, and then in the past, some t up to t seconds in the past B, and up to t seconds in the past before that C. So I represent this as a signal processing chain, right? Reading from the inside out, this here, underneath each box, I'm representing the first order response. So this is the response of C. This here is the response of once C. This is the response of B. And these now take care of this first end. So this here is the first order response of this subformula. Again, we take A. This is the response of A. This here is up to here is the response of once this entire thing, and so on and so forth. So you just build it up pretty much in the way that you write it. And at the end, you get the first order frequency response of the entire formula. Now, if a signal processing person walks into the room right now and simply sees the diagram, they understand what's going on in the frequency domain. They can say, yeah, I know how to interpret frequency responses. They don't even need to know about the formula. And this, to me, is kind of the beauty of this. It is that we have one language using the Volterra series and their frequency responses to treat logical operations, such that robustness, and other signal processing operations that look at frequency. Now, finally, how do I apply this? So we can do this as an analysis step. And I should say here, we are not suggesting that you throw away your existing monitoring algorithms and replace them with Volterra series. Volterra series are an analysis tool. So how can we use this analysis? We can do monitoring-aware filtering. So what I'm showing you here in red is the original signal you want to monitor. In blue is a compressed and reconstructed version of that signal. This compression was done in a monitoring ignorant manner. If you look at the robustness of red and blue, they are significantly different. Right? This here is the robustness of the two signals. They are significantly different. And in fact, at some points, one says the formula is satisfied, the other says this formula is violated. But using the analysis we just presented with the help of Volterra series, we can do monitoring aware filtering. So again, red is the original signal, blue is the compressed and reconstructed signal. We did this manually. We looked at the frequencies that are relevant to this formula. I believe this is historically seen. We looked at the frequencies that are relevant to the formula and made sure we preserved them in the compression operation. So we obtained a nice compression effect, but if you look at the robustness signals, they are practically indistinguishable. So we achieved compression without sacrificing monitoring accuracy. And this is the sort of thing that you can do once you have an understanding of the frequency content of a temporal logic formula. The overall project being, again, logical signal processing. Thank you.
So, yeah, thank you very much for this nice presentation. We have a question session now. So there's one question from Slack. I would like to ask Gio maybe to ask himself live.
So, Hussam, I think the later part of your talk touched upon this topic well, but I was wondering if there is a sense in establishing some kind of a correspondence between frequency content of a signal and the frequency content of the robustness signal corresponding to the BB Steele formula.
So
I'm not sure if your paper already does this. Yeah.
So a sense of correspondence. So Niraj is also online, by the way. If Niraj, why don't you go ahead? My student is online, so. Maybe not. Okay, I'll jump in. Sense of correspondence between the frequency content of the input signal and the frequency content of the robustness operator. Is that the question?
Yes.
Yes, so, I mean, I guess it depends what the questioner means by correspondence, but the idea here is that the robustness operator suppresses certain frequencies, enhances others, and keeps some just the same, right, from previous content. So the idea here is that if the robustness operator suppresses frequencies in the band 5 to 10 hertz, for example, then you don't need those from the input signal. You can throw them away, thus achieving memory savings, for example, right? I don't know if that answers the question.
It partially does. I guess my question was, does your paper establish some kind of a theorem that shows systematically how you can analyze this? It looks like from the latter part of the presentation that you kind of did this for the case study.
So it is possible to do. It is possible to do now. In this paper, and as we mentioned in the paper, we did it manually, meaning we looked at these diagrams and we said, well, there's a big zero over here, so we're going to discard this stuff. But this is actually something we're doing for the next paper, which is basically to automate this detection of relevant and irrelevant frequencies. And if it's for linear systems, it's bread and butter. It's very easy to do. For the Volterra series, it takes a little bit more work because of the nasty integral in there, but this is something we're working on.
Thank you. I think I've seen Oleg raising his hand, actually.
Yeah, so my hand is down. So Hussam answered my question already. It was about whether you can do this analysis automatically and come up with a compression scheme, and looks like he's doing that next. So I'm looking forward to his next paper.
Thank you.
Okay, and maybe one last question from Laura. Laura, would you like to ask yourself?
Yes, but I think also my question was about the implementation part. So I was asking, because to have the monitoring procedure of this atomic proposition, you need to compute the integral, no? So I was thinking how much was costly this procedure in the new logic. Yeah.
For computing the atoms, this is something we have because it is part of the logic semantics. Your task as the designer is to pick the relevant atoms, the measurements you want to make. And they have to be linear measurements because they are integrals, unlike more general STL, where the measurements can be any arbitrary function mu. But this is part of the logic we have. For example, we're using Gaussians in the experiments in the paper. You can use others. Although there are some very good theoretical reasons for using Gaussians, but which are out of scope now.
So I suppose these were all the questions for the speakers. So thank you very much for this nice presentation. I would like to continue with the second paper for today. So the second paper is written by Thomas Wright and Ian Stark, and this is entitled Property Directed Verified Monitoring of Signal Temporal Logic. So let's start with the presentation now.
Presenting Property Directed Verified. Hello, I'm Thomas Wright, and today I will be presenting Property Directed Verified Monitoring of Signal Temporal Logic, which is joint work with Ian Stark. The problem we will be interested in is verifying behavioral properties of a continuous or hybrid system. Two popular approaches are first the STL monitoring over numerical simulation traces produced via a numerical method, or secondly, applying a reachability analysis tool such as FlowStar, which is usually restricted to a smaller class of reach avoidance property, but gives exact formal verification results. Our aim is to work on a combination of these two approaches, which produces exact formal verification results for STL properties using FlowStar flow pipes. So, our approach. We'll look at a free-valued extension of the STL monitoring algorithm. We'll see how tight integration with FlowStar's flow pipe representation allows us to give the most precise results. We'll then turn our attention to optimizations of this method, first the adaptive symbolic composition, and then masked monitoring. FlowStar verification starts off with some model of the system we want to verify. So, for example, we could have this system of differential equations with an uncertain box of initial conditions. Then FlowStar produces a flow pipe which encloses the behavior of this system over time. In order to understand our method, we first need to dig into FlowStar's flow pipe representation, which is based on preconditioned Taylor models. Classically, interval arithmetic allows for verified numerical methods by replacing floating point values with an interval range of uncertainty in the values. Taylor models allow us to over-approximate a whole function, in this case f, by taking a polynomial p enlarged by an interval range of uncertainty I of the value, and this can then enclose f over an entire time domain. Similarly to interval arithmetic, we can perform arithmetic operations on Taylor models, but we are able to get more precise results due to the use of symbolic operations. Taylor models also extend naturally to n dimensions as Taylor model vectors. Whereas a classical numerical method would give us a function value at a number of time points, a FlowStar performs verified integration to give us a Taylor model or flow pipe segment for each time step, which then gives a Taylor model enclosing the possible range of the function. In fact, FlowStar's flowpipe format is richer still and gives something called preconditioned Taylor models, which actually give us two Taylor models, the first acting as a transformation of the state space and the second the actual solution. And these are symbolically composed, which we denote with this square by substituting the first into the second to give the overall Taylor model. So, our method. The original STL monitoring algorithm of Mahler and Nikovic used Boolean signals for propositions which can then be combined for monitoring complex propositions. We use free-valued signals which map each time point to either true or false, or also the third possibility, uncertain, where we do not have enough knowledge to either refute or verify the proposition. These are represented by a number of intervals and Boolean values of the signal on each of these intervals, and we assume all the gaps in between are unknown. Then, in order to handle complex propositions, we can manipulate these. So, for example, we can take negation by negating all of the Boolean values on each interval. For complex propositions such as and or, we can also combine signals to get a signal for them. And for temporal operators such as finally, we can handle this by an appropriate backwards time shift for each type of interval. The until operator is a little harder, but we can handle this also using an appropriate free-valued decomposition. When we wish to monitor an atomic proposition, which is given as a polynomial inequality featuring a polynomial p over the system variables, we need to first get a handle on the value of p over a particular flowpipe segment. We can do this by taking a symbolic composition of Taylor models, both the two halves of the flowpipe and the polynomial p, which gives us an interval function. We can then apply interval root finding to this to give bounds on the uncertain regions of the signal, and then fill in the values in between just with interval evaluation. So our overall verification procedure proceeds first from the flow start verified integration. Then we must compose the two halves of each of these flow pipes. And then we compose this with the atomic propositions. And finally, we need to apply interval root finding. This is sufficient for verification of the full range of STL properties, but it may be expensive given these symbolic composition operators are expensive as they involve symbolic operations on high-dimensional Taylor models. Also, a flowpipe may consist of thousands of flowpipe segments, adding further cost. So we now turn our attention to optimizations to make this method much more efficient. Firstly, we have the problem that we may be doing more work than is necessary to determine the Boolean value of the signal. This arises because as we apply all of these symbolic operations to get the most tight bound on the function value, whereas we only need to know the Boolean signal value. Our solution to this is adaptive symbolic composition, which relies on the observation that for a cruder over approximation of the value of p, we can replace these symbolic operations with ordinary interval function composition here, which gives a cruder over approximation of the function value, which is much cheaper. We can then progressively reintroduce symbolic operations as needed to determine the signal result, which already gives a big saving to the cost of monitoring. However, we are still limited by the very bottom-up nature of our monitoring procedure, which requires us to, in order to verify a complex proposition, then we first monitor the atomic propositions to the maximum precision possible before then combining them to deal with the complex proposition at hand. This is perhaps unnecessary because as a given complex proposition may only depend on its atomic proposition on a small time domain. For example, if we want to monitor f between 5 and 6 phi at time t, then we only need to look at phi between 5 and 6 time units in the future. Whereas if we want to monitor phi or psi, and we notice that phi is true at a given time point, then we don't need to look at psi at all on that time point. Our solution to this problem generalizes this reasoning and is called masks. So the aim of mask monitoring is to supplement this existing bottom-up monitor procedure with top-down computation of masks, which record regions of interest for a given property. So a mask consists of a sequence of disjoint intervals and in fact represents a Boolean signal for the region on which we want to know a given property. So if we're given, for example, a mask for a complex property fj phi, we can then push this mask down through the property to get a mask for phi using an appropriate forward time shift. Or for OR, if we first monitor a signal for phi, we can then pass this down as to find an appropriate mask for phi. And when we reach the atomic propositions, we are able to restrict the monitoring for the atomic proposition by restricting the time domain to the regions inside the mask. In particular, this allows us to completely avoid symbolic operations for flow pipe segments outside of the mask. So overall, masks allow us to skip every step of the monitoring process apart from the actual verified integration outside of the region on the mask. Finally, we will look at an example and some performance results. So we looked at this Flowstar benchmark system, which consists of a 9-dimensional initial value problem consisting of 9 nonlinear ODEs and a 9-dimensional box of uncertain initial conditions, here shown in red, projected down to 2 dimensions of interest. And the property we're interested in is phi, given by 2 atomic propositions. The first P is this orange half space, and the second Q is this green ellipse. So when we applied our monitoring algorithm, we derived the following signal, which is sufficient to verify that phi holds at time 0. And in the paper, we compare a number of different variations of our algorithm to assess the performance impact of each component. We found that symbolic composition for Q was indeed necessary to verify the overall proposition. So if we look at our cruder functional composition over approximation of the value for Q, this gives a much wider range of uncertainty, which proves insufficient for verification. When we applied an adaptive symbolic composition for monitoring P, this saved on 70% of the monitoring cost. And when we reach Q, using an appropriate mask saves 60% of the total monitoring cost for the whole property. So, in conclusion, we've designed and implemented a complete verified monitoring algorithm for STL using Flowstar flow pipes and free-valued signals. And we found that our use of symbolic operations throughout was crucial for the most precise monitoring, but for performance we need to use this wisely via adaptive symbolic composition and masks. For future work, we note that our existing method currently only uses part of the information contained in the Flowstar flow pipe, as flow pipes don't just track the state of the system over time, but how the state depends on the initial conditions of the system. We can use this as an efficient way to construct spatiotemporal signals which have refinements of the initial conditions as their space domain, and in fact use a spatiotemporal extension of masks for efficient monitoring. Thank you.
Okay, I suppose our presentation for this paper is finished. So I think Abbas has a question. Yes, Hussam, sorry.
Yes, no worries. Thank you for the talk. It sounds like the idea of masks is applicable to monitoring classical semantics as well. I mean, like not just over flow pipes.
So it may be applicable in this case, but the cost profile is a bit different in our case because the actual monitoring on the atomic proposition is much more expensive compared to the other operations as in the classical case. But also in the classical case, online monitoring could give some of the benefits that we get with masks, but I'm not sure. Yeah, we're mostly interested in this special case where you have this unique feature that actually the trace we get from the system is itself very expensive to evaluate at a time point.
Right. Thank you.
Thank you. So do we have any more questions for this paper? If not, I would like to ask one interesting question. So when I saw the concepts of using masks, it kind of reminded me, I think actually Dan was doing something similar in his PhD, one of his papers for the PhD thesis, where he actually monitored, where he implemented STL monitoring algorithms for continuous time with the intervals. So question both to Dan and to the others. So does this have any similarities with your work, or are you aware of these algorithms for continuous monitoring of STL with the interval marking? I think I remember this was the kind of algorithm he used.
I'm not sure which exact monitoring algorithm you're referring to. This is an extension of the interval-based monitoring algorithm for continuous time, which was Boolean signals. And we use a similar representation using intervals, except the difference is we handle the uncertainty using pre-valued signals. I don't know if that is what you're referring to.
So in my understanding, your idea of masks is to narrow the scope of where you are going to do the operations, and this is different. Like you say, this is something that we don't really need when we are monitoring a single signal, but which makes a lot of sense if you are monitoring the entire flow pipe. At least this is how I understood it.
Yes, I think that agrees with my understanding. Thank you.
Thank you both of you guys. Thanks. All right. So do we have any more questions for this paper? So if not, I would like to continue with our next presentation. This is a work entitled "Verified Online Formally Verified Monitor for Quantitative Temporal Logic," written by. Presented by Agnishom Chattopadhyay from Rice University. We can start the video.
Graduate student in Rice University. I am Agnishom Chattopadhyay, a graduate student in Rice University. I shall present the formalization of a monitoring algorithm for quantitative metric temporal logic. This is joint work with Konstantinos Mamouros. Often we expect the behavior of cyber-physical systems to satisfy certain specifications. For instance, an aircraft operator might be interested in making sure that the aircraft never reaches a high velocity at a low altitude. An online monitor is a device which interprets such behavioral information in real time to check whether the system is behaving in accord with the specification. Since these monitoring algorithms are mission critical, it is important that we have confidence in their correctness. To this end, we discuss our formalization of a monitoring algorithm in the proof assistant Cork. Let us start by reviewing temporal logic on which our formalism is based. Here we have a collection of atomic propositions, and our formulas will be interpreted over traces, which are finite sequences of valuations of atomic propositions. By way of introducing some notation, we will use the notation W subscript minus K to denote the trace in which the last K valuations were removed. Atomic propositions are interpreted using the most recent valuations of the trees. Boolean connectives and or are interpreted in their usual way. We say historically S to indicate that S is true in every valuation of the trees. Similarly, we say in the past R since R was true in some valuation of the trees. We use the abbreviations H and P to refer to these modalities. Here, we say S since R to point out that R has happened sometimes in the past and S has been happening since. In the metric version of the temporal logic, we annotate our operators with intervals. For instance, we could say that we are specifically interested in an R that occurred within 2 to 4 steps. Instead of Boolean valuations, our traces may sometimes contain numerical information. In this case, we look at predicates which compare the components of our traces against constants in place of atomic propositions. Temporal logic formulas classify behaviors as either correct or incorrect. Even among correct behaviors though, certain behaviors may be more desirable than others. For instance, we may ask how much perturbation would be acceptable in our signals. This problem can be made rigorous by endowing the space of traces with a distance function. One way to approximate the answer to this problem is to consider a quantitative semantics where disjunctions are replaced by supremum and conjunctions by infimum. In the general setting where we define our semantics, the traces are finite sequences of values from some arbitrary domain. The set of truth values form a lattice, an ordered set with an well-behaved infimum and a supremum, called join and meet respectively. We want our truth values to have a largest element top and the smallest element bottom, and we also want meet and join to distribute over each other. We have a set of atomic predicates, which are functions from the domain to the lattice of truth values. Propositional temporal logic fits into this setting. Here, the traces are sequences of d tuples of Boolean values, where d is a number of atomic propositions. The lattice of truth values consists of true and false, where and or take the role of meet and join in that order. The predicate projects out specific valuations or the negations of each tuple. In the case of signal temporal logic, traces are sequences of tuples of real numbers denoting components of a signal. The truth values are either real numbers, potentially including positive or negative infinity. The predicates consist of a comparison operator, where the operator xi greater than c is interpreted as the value xi minus c. Given a trace and a formula, we shall define the corresponding robustness denoted ρ. For atomic predicates, we define the robustness of a trace by evaluating the predicate on the latest event. Or and are interpreted by treating them as join and meet respectively. P sub I of phi is interpreted as the finite meet of the robustness values of the trace fragments in the specified interval. H is also interpreted in a similar way. The interpretation of since is analogous to the usual case, where conjunction and disjunctions have appropriately replaced by meets and joins. We also use the dual of the since operator, which is defined by dualizing the operators in the definition of since. We use Moore machines to formalize the idea of algorithms. These are stateful machines with an associated output at every state, which we call mout. The state is updated as the machine consumes more input using the mNext function. In our formalization, we use a co-inductive definition where the state is not made explicit. Instead, the machines are identified with their output and how they evolve. An online monitor incrementally produces judgments on the trace prefixes that it has seen so far. Feeding in the elements of our trace to Moore machine would yield a similar behavior. when indeed the output of the Moore machine M corresponds with the robustness values of the trace fragments seen so far, with respect to a formula phi, we see that M implements phi. Let us say that the monitor M which implements a formula psi and the monitor N which implements a formula phi. We can consider a monitor which internally runs a copy of M and N and considers the meet of their outputs and steps both M and N parallelly when an input item is available. This gives us a way to combine M and N into a monitor which implements the AND of two formulas phi and psi. We call such constructions which compose given Moore machines combinators. Our approach in solving this problem is going to be by building a library of combinators. We have already seen the combinators corresponding to logical AND and OR. In a similar way, we intend to build combinators for every logical connective we have. As a base case, we have the atomic predicates which can be lifted to a monitor simply by computing the corresponding function at every new input. Consider the temporal connectives where the associated interval is unbounded. For instance, consider P. The robustness values of P phi is simply the join over all the robustness values of phi. Thus, as our state, we can record the running join of the robustness values seen so far, and when a new item is available, we need to simply update our state by taking the join with the robustness value of the new element. Here we have a snippet of Cork code illustrating this idea. M4 docs, which takes a Moore machine M, a binary operator OP, and an initial value ST. It produces the running aggregate of the outputs of M with respect to the operation OP starting with ST. By appropriately choosing the initial value of the operation, we could use it to define M sometime corresponding to P and M always corresponding to H. Even with sins, we have a well-known identity in the literature that allows us to express how old values of sins can be reused to obtain newer values. Turning our attention to bounded temporal connectives, we see that they can be decomposed in the following way. Here, PA is short for PAA, which indicates what happened exactly A steps ago. We can simulate the behavior of P sub A using a queue of fixed size A, which emits the enqueued values after A steps. In Cork, which is a functional programming environment, reasoning with stacks or functional lists are easier. We use two stacks to emulate a queue. We call one of them rear and one of them front. Suppose we wish to enqueue the element A. Enqueues are always done by pushing to the rear stack. Dequeues must happen from the front stack. The front stack is empty right now, so we shall reverse the contents of the rear stack and place them in the front stack. And now elements from the front stack can be removed directly. If we need to dequeue again, we do not need to reverse the rear stack again until the front stack is empty. In summary, dequeue may trigger reversal of rear, which takes time proportional to the number of elements in rear. However, the cost is amortized, and on an average, it is only O of 1 time per element. The other piece of this decomposition is P0, K for some constant K. Let us look at how to handle them. P sub 0, K is the finite join of the last K robustness values. This could be thought of as computing aggregates over a sliding window of fixed size K. To compute sliding window aggregates, we use a data structure similar to the queue implemented with two stacks. Additionally, we keep two stacks which records the aggregates of the rear and the front stacks. The actual aggregate can be found by combining them. As before, dequeues may have some latency occasionally, but the cost is amortized so that every operation takes O of 1 time. Thus, we can deal with P and H by either computing an aggregation over the entire stream or a delay combined with a sliding window aggregation. We need to deal with sins and its dual. This is easy when we have an unbounded interval. Otherwise, we can rewrite sins using a delay operation. However, we still need to deal with sins 0, K. Since 0, K does not appear to be a sliding window aggregation, but fortunately we can rewrite it in terms of 1. This identity is easy to see for the Boolean semantics. Here we are additionally adding the information that psi must have occurred within k units in the past. The identity also happens to be true in the general setting of a lattice. Thus, we have found a way to translate each connective into a combinator. We have a collection of combinators, one for each connective. Some of them, like those for P and H, need to maintain a buffer and consume space proportional to the constants that appear in the formula. This consumption of space is unavoidable. However, the time that each of them take per item is O of 1 and independent of the constants in the formula. To construct the monitor for a given formula, we recursively traverse the structure of the formula, replacing each connective by the corresponding combinator. Let us look at one of the combinators now to understand the process of verifying them in some more detail. We have mlift, which takes a value in it and a function f. It starts with the initial value in it, and given successive elements, it applies the function f on them. In our case, we wish to use the bottom as initial element. The lemma m atomic underscore correctness states that given any formula f, m atomic implements the corresponding atomic predicate. To prove its correctness, we require two lemmas in turn. The first one is about state. Here G next denotes the state of the machine, which is obtained at the end of feeding in an entire trace. We wish to say that at the end of the execution, the machine we obtain is still a machine which is of the form mlift, where the state has been replaced by fx, where f is the latest value. We also use the lemma mlift underscore final to state that the result at the end corresponds to the value f of x. Recall the definition of m for locks, which we use to implement m sometime and m always by computing running aggregates. Here we see that what the correctness lemma corresponding to the m sometime operator should be. To prove it, we need to make claims like before about the state and the result the machine produces after consuming an arbitrary trace. We extracted OCaml code from our Cork proof scripts and ran some experiments on them. We compared the performance of our tool with relay using formulas from the timescales benchmark and the randomly generated traces. We see that our tool performs reasonably efficient. Some of the combinators which we used use buffers to store values. We measured the performance of this tool with formulas with different constants. As we expected, the deterioration of the throughput for our tools is comparatively negligible with the growth of the constants. In summary, we discussed a lattice-based framework for quantitative semantics for temporal logic, formalized the notion of online monitors as Moore machines, and used Moore combinators to construct monitors. We have verified this construction in Cork and extracted OCaml code, which performs reasonably well. Thank you for listening.
Thank you. For some reason, the videos always finish a couple of seconds before the end. But okay. Yes, this is the Q&A session. So, do we have any questions for this paper? Let me check out the Slack channel. All right, no questions there. So, if not at the moment, I would like to ask one question. Actually, I would like to ask the question about the memory consumption of your monitors with respect to changes with the formula bounds and with the different formula horizons. Actually,
so there are formulas like P and H which have constants that appear in them. So the memory consumption is proportional to the constants that appear in the formula, because we essentially store a queue of that size. Otherwise, for most other combinators, it's just O of one space.
Thank you very much. Do we have any questions from the participants? I don't see any questions. So thank you very much.
Yeah, thank you.
We're good in time. I think we can proceed with our with our next talk. The fourth talk of this session is actually about Moonlight, a lightweight tool for monitoring spatio-temporal properties. And our speaker today will be Michele Loretti from University of Camerino, Italy. So please start the presentation.
Hello, my name is Michele Loretti, and in this talk I will present to you Moonlight, a lightweight tool for monitoring spatial-temporal properties. In our life, we are surrounded by a huge amount of interconnected devices. These devices sense data from the environment and are distributed over a physical space. A number of applications and systems have been developed to use these devices in order to reach complex goals. However, to monitor the correct behavior of these systems, of these applications, we need tools that are able, from one end, to speak about the spatial and the temporal aspects of our systems, and where data types play a central role. For this reason, in the recent years, a number of proposals have been done to define formalism that allows us to specify spatio-temporal properties. One of these proposals is STREL. STREL is a formalism that extends signal-temporal logic with two new spatial operators that allow to specify properties about reachability, that is, the ability, starting from a point, to reach another location in the space, and escape. This is the ability of starting from a point and escape from a given region while a given formula is satisfied. STREL formulas are interpreted over spatial signals that may take value over different general domains. General domains represent general data types. The evaluation of STREL formulas is parametric and can take into account different kind of domains. And then we can consider Boolean domain, for instance, if one is interested in qualitative semantics of formula, while if one is interested in robustness, we consider reals domain. Moonlight permits monitoring STREL formulas, and the tool is able to monitor just temporal properties in STL-like formulas and spatio-temporal properties. We have developed a script language that simplifies the specification of the properties and the declaration of the expected signals. We have developed the tool integrates a number of interfaces that permits using Moonlight within MATLAB or Python, or can use the tool via a console. The tool is developed in Java and can be easily extended and integrated in other applications. Finally, Moonlight is available at the following link to a GitHub repository. Now let me show you a short overview of the Moonlight architecture. At the center we have the core API where you can find all the features implemented in Moonlight. Together with the core API we have a compiler. The compiler just takes a script. The script is a formal description of the signal we want to analyze, The space, this is a script for spatial temporal properties. Then we have the structure of the space, and in particular the kind of values we can have in the edges in the space, since space is modeled as a graph, and the domain we want to use to interpret formulas, and the list of formulas we want to consider. The script is passed to the compiler, and the result of the compilation is a Java class that uses the core API to perform the monitoring. In order to access to the Moonlight framework, we have these front ends, in particular Python, MATLAB, and the console. This is a piece of code of a MATLAB script that can be used to interact with Moonlight, where we can see that we can load a script from file. Then we can get the monitor associated with a given formula. We can set some of the parameters, and then after we have defined the specific domain, we can perform the monitor. The spatial temporal monitor takes as an input a spatial temporal trajectory. This consists of a sequence of weighted graphs describing how the topological configuration changes in time, and a set of signals describing the values at each location. Of course, if we are considering just a temporal monitor, the input consists of a single trajectory or a single signal. The output of the monitor can be adapted to specific domains, and then we can use Boolean, as I already said, if we are interested in qualitative semantics, and then just a yes-no satisfaction, or a real domain if one is interested in quantitative semantics, where we have the robustness of the formulas. To evaluate our tool, we considered a benchmark proposed by Oxa et al. In a recently published paper, where a MATLAB Simulink model is used to describe an automatic transmission. We monitor for requirements of the proposed scenario, and then we contrast the results obtained with Moonlight with the other two well-known tools that are Bridge and Estaliro. These are the results of the evaluation, and you can see that Moonlight works quite well and at the same level of the other two tools, and in some cases Moonlight performs better. The evaluation in the paper, you can find also a description of a spatial temporal monitoring, and in this case we considered a wireless ad hoc sensor network scenario, where we have three types of mobile devices that are coordinator, router, and end device, and each device is equipped with a battery. For each network, there is only one coordinator that is responsible to initialize the network. Routers are used for passing data from one device to another, and devices can only communicate with routers or with the coordinator. So, Moonlight can be used to evaluate different properties describing the requirements of our scenarios. Here we consider just a single example, while other properties with all the details are available in the paper. In this case, for instance, we can check if each node can reach another device in less than k ops, where the battery is eventually greater than 0.5. These properties guarantees that, if satisfied, guarantees that a message can travel in the net at distance k without any problem, since the battery is over a given threshold. Here we have a table with the evaluation. Spatial temporal trajectories are generated via MATLAB script, and then we evaluate the formula with a number of devices ranging from 10 to 1000, and by considering different steps in the formula. You can observe that there is not a real difference in the Boolean and quantitative semantics. Some concluding remarks. So we have presented the Moonlight, that is a simple and quite flexible monitoring tool that supports both temporal and spatial temporal properties that can be used to verify and monitor properties of mobile and spatially arranged cyber-physical systems. The integration of Moonlight with MATLAB and Python enables the use of our tools in other tool chains, and this is an important feature. In the future, we plan to add more sophisticated and usable graphical user interfaces, and to extend the tool with new functionalities, such as the support of parallelized and online monitoring. Thank you for your attention.
So thank you for this interesting presentation. Yes, do we have some questions from the audience, from the participants? Okay.
I do.
Okay, please go ahead.
Thank you for the talk. So in the logic ST-REL, the spatial operators, are they, what sort of geometry do they assume? Are they continuous space operators, or is it over discrete grid space, for example? And if it's continuous, what do you allow? Is it only polytopes? Is it something more general?
So the operators are, so the graph, the space is in fact discrete. So you have, it's described in terms of a graph. And in some sense, both the operators speaks about the structure of the graph, and the properties of the path in the graph. And then the intermix of temporal and spatial operators allows us to speak about how this structure changes in time. And as we have observed, the two operators are quite general and allow us to represent other existing proposals in literature about spatial properties. In any case, properties are in some sense discrete, even if you can speak about values that may have a real domain.
Okay, thank you.
You're welcome.
Thank you. And I would like to ask a question related to the evaluation results. So in the evaluation table, I think you actually varied the number of devices between 10, 100, and 1000. But did you vary the topology of your system, or you actually were evaluating topologies like in the example where you have one central or two central devices and others are connected to this?
So the topologies change in different simulations, because these are models that are generated by MATLAB. So of course the structure is different, because you increase the number of devices, and then the topology is changed. What we consider as a space is, of course, the connectivity graph. So there is an edge among two devices if they can interact with each other directly. The two are in the same range of communication. I have to have answered to your question.
Thank you. And one more question. If you could give a comment, maybe for the future work you mentioned, you would like to work on online on an online approach, right? And I was wondering how hard, how big is the gap which needs to be bridged between your current version of the tool and an online version?
So moving to the online monitoring in this context is not easy in some sense. So the first step we are working on is considering a signal where the different values of the different locations arrive at the same time. So you see the spatial signal evolving in time in some sense. And this is reasonable and easily integrable in the tool, because thanks to the generality of the approach we have used in the Java classes we have developed. The next step that is quite challenging is developing an online monitoring where data are not synchronized and may arrive from the different devices at different time. And of course, the last step is having a fully distributed monitoring framework, where each device is able to monitor the property by itself. And this is really, really hard to be achieved, this result.
Thank you very much. Do we have some more questions? Okay, let me check the Slack channel. All right, no questions there. So thank you very much one more time, and let's proceed with our last paper of this session. So the work is entitled TLTK, a toolbox for parallel robustness computation for temporal logic specifications, and will be presented by Joseph Crawley from Southern Illinois University. Please start the presentation.
Greetings, everyone. My name is Joseph Crawley. This is joint work with Aranias Pantiti at SIU, Bharat Hoxha from Toyota Research Institute of North America, and Georgios Fanekos at ASU. And today, we are going to present TLTK, a toolbox for parallel robustness computation for temporal logic specifications. First, we would like to go over some preliminaries. The theory of robustness of temporal logics has been utilized in a wide array of problems, from testing and verification of cyber-physical systems to monitoring and planning for autonomous systems. It enables the formulation of the problem of finding system behaviors that do not meet system requirements as a falsification problem. Given a model of a system and a specification, a falsification tool will either succeed at finding a counterexample or run in times and report that no counterexamples are found. However, there is no guarantees that a model satisfies the specification. The specifications may be defined in temporal logics such as MTL and STL. An example of such a specification for a fault-tolerant control system is seen here at the top right. It says the fuel flow rate should not be 0 for more than 1 second within the next 100-second period. This is represented with the following STL formula. Given a trajectory of the system and the STL specification, we can calculate the robustness, which represents how much of a perturbation the input signal can take before the Boolean valuation is changed. Now, an overview of our tool. TLTK is designed to work with 3 separate modules. First would be a system or system simulator to generate a signal to be used in the robustness calculation. The output from the system simulator needs to be the output signal it produces and the timestamps that each signal tick was generated. This data gets used by the robustness computation engine that returns a robustness for the signal passed to it based on an STL formula given to it. The robustness calculation engine can take advantage of parallel processing to scale correctly on modern hardware. The main interface for the robustness computation engine is made in Python that wraps code written in C for fast robustness calculation. All the operations are represented by Python objects, where new STL operations can be added by adding new Python objects. The final module that TLTK works with is the stochastic optimizer. This is used to change the inputs into the system simulator to minimize the robustness returned by the robustness computation engine. There is an implementation of a stochastic optimizer used to change the inputs and initial conditions of the system with the goal of minimizing robustness. Here we will look at a figure whose left-hand side has a visual example of a two-dimensional signal mu, a set R1, and an initial condition set x0. The robustness is calculated over the STL formula, globally not R1. First, all the distances are computed from the set R1 and the signal points mu. In TLTK, the distance calculations are evenly spread between threads. Next, we calculate the NOT operation in the STL formula by multiplying all the distances by -1. Finally, the global operator gets resolved. This operation searches for the max negative distance, which is shown on the right-hand side as a red line rho star. TLTK works by using a sliding window technique when calculating robustness. In this example, we will illustrate how to use parallel computation to compute the robustness. First, the row that contains R1 is computed. We can see it gets divided into two threads, represented by blue and orange. The threads compute R1 right to left, as so. Next, R2 is divided into threads the same way R1 was, and then it is processed. After that, the AND, NOT, and global operation are divided and processed in much the same way. In this figure, there is an example of how a sliding window works for time-bounded formulas in TLTK. Assume we want to calculate the temporal operation finally for the shown signal. We start by searching for the max value starting from the end of the signal and move towards the beginning. On this section, we initially search the signal for the corresponding area indicated by the dotted window. The max of this search is indicated by the green X mark. The next window is going to be located one time step to the left. Since the max is located outside of this signal area, we will have to search the whole signal segment indicated by the red box. Therefore, in this window, the max is located on the top left part of the window. Section B illustrates a different example. The area that we searched for the max value in the previous window position overlaps with the current window position. Additionally, the previously found max value is contained in this overlapping area. Hence, we do not have to redo the search for the whole signal segment indicated by the solid blue box, but only for the part indicated by the red box. Finally, in section C, we show another possible case. The max value we found in the previous window position is again in the area that overlaps between the past and present window. Once again, we will not have to search the entire blue box for the new max value. However, in this case, the signal segment we're searching already contains the max value found. In this case, we have to update the max value with the one found in the current window position. TLTK allocates and deallocates memory when needed to attempt to keep its memory footprint as small as possible. In this example, we will work through the methods it uses to conserve memory. In the top left table, we see the inputs into TLTK, which are the timestamps and the two signals. In the top middle table, we see the distance calculation from the signal R1 to the set that defines R1. These distances overwrite the row of the signal given to it. Next, the NOT operation is calculated in place over R1. Then, in the bottom left, the distances are calculated for R2 and stored in the row R2. After that, NOT R1 and R2 is calculated and stored in the row that contains R1. After the AND operation, the row R2 is deallocated as it is no longer needed. In the final table, in the bottom right, the eventually operator is processed. A new row needs to be allocated to store the results. Then, after the operation is complete, the row that contained the result of the AND operation is deallocated. In the following slides, we will show our evaluation results. We test TLTK against two state-of-the-art STL robustness calculation tools, dptalero and Breach. Both have a MATLAB interface for the end user. We note that both stalero and Breach have a sequential algorithm. We use a parallelized algorithm in these results. We compare TLTK with Breach and dptalero separately so that we may focus in the areas where they have the strongest performance. We use 3 specifications of different length and number of operations to test the computation speed. The results on these graphs show a 30 to 400 times improvement in computation speed. In the highlighted example, TLTK performs 50 times faster than Breach on a signal with 2 to the 10th or 1024 time steps. The reason why TLTK's line is longer in these 3 graphs is because Breach uses more RAM than our test setup has and crashes when processing these larger signals. In our comparison with dptalero, we utilize specification from benchmark problems, in which we look at increasingly large sizes of formulas and predicate representations. Again, we will look at a signal with 2 to the 10 or 1024 time steps. TLTK performs the operation in 0.0023 seconds, and it takes dptalero 1.58 seconds. This puts TLTK 686 times faster than dptalero in this example. Finally, we will look at 2 to the 22nd or 4 million samples, where TLTK does the operation in 6.4 seconds, and dptalero runs out of memory. TLTK is available for download right now. It is available in Linux or Windows through Docker. There are 3 ways to set up TLTK: through Docker, Python, and Git.
Okay, thank you. Thank you very much for this interesting presentation. So let me see if we have a question from the audience. On our Slack channel, no. Here we also don't have any questions for the time being. So let me ask the first question myself. So as far as I understood, your performance boost is significant, and it's coming actually from 3 different kinds of sources. On one hand, you use GPUs, parallel machines, right? On the other hand, you also manage the memory resource as well. And on the highest level, like on the algorithmical level, you actually split the workload between those threads, right? So you basically optimize on different levels of complexity, let's say. Is this correct? Did I understand this correctly?
Yes. We also optimize reused information on the temporal logics with that sliding window, whereas as far as we know from dptalero, they recalculate a lot of that stuff over and over again.
Okay, cool. Thank you. And then I also want to say I've read the paper, and in the paper you mentioned you want to use the tool for planning and control of robotic systems. So I was wondering, is your toolbox ready to be deployed to such a use case, or you still need to implement some features to bridge the possible gap?
It has a full Python interface currently, so if anyone want to use it for the robotics applications, they can use the Python interface.
Let's see. Okay, so we have a question from Slack. So I would like to ask Thomas to ask his question in live.
Hi, thank you for your talk. I was just wondering, when you're performing this sliding time window optimization, do you have any intuition for processing the optimization right to left, as this seems slightly...
Yes, yeah, we start at the last time step and work our way backwards in time. Each thread has their own implementation of a window moving backwards in time like this.
Okay, but is there any reason why you go backwards in time as opposed to forwards in time? Because, for example, if you wanted to do some of this online, you'd receive the information in the direction.
It kind of comes about because you process from 0 to infinity, you process that backwards in time like that. So it just made it easier to reuse some tested code to also do time-bounded temporal logics backwards in time like that.
Okay, thank you. That's a better question.
All right, thanks. Do we have some more questions from the audience? All right, I don't see any of new questions incoming. So if not, then I think we can conclude today's temporal logic session of the RV conference. I would like to thank you for your attention, and I would like to invite you to enjoy the rest of the conference.